Plus, from this lecture onwards, we will give you an introduction to the notion of integral calculus. In particular, here we will talk about Riemann integration, which will in some sense be consistent with the notion of area of a region which is bounded above by a curve, as we have seen in my previous video. So I call this region RF. A proper description is given here. So what do we need here? We need a, b, two real numbers with a less than b. We need a bounded real valued function f, which is defined on the closed interval ab. We will always remember that throughout this course we will only be interested in bounded real valued functions. So this will be always at the back of our mind. Now let's go forward. Our goal is to make sense of this definite integral which is given here, and we would also like to have that integral fx as x runs from a to b is same as the area of the shaded region. Now what is the first step that we used in order to calculate the area of this region? First, we divided the base of the region into several parts. This leads us to the notion of partitions of an interval. A partition of a closed interval AB is a finite ordered set. So let me call this set P. It consists of n plus 1 points. And what do I mean by an ordered set? We simply write the elements of the set in increasing order. The first element will be equal to A and the last element will be equal to B. You may notice that a partition which has n plus 1 points divides the interval AB into n parts, not necessarily equal. What are the n parts? So here first part will be x0, x1, where x0 is equal to A, x1, x2, x2, x3 and so on. The last interval would be xn minus 1 b, which is same as xn minus 1 xn. The interval given by xi minus 1 comma xi is called the ith subinterval. Let us see an example, a concrete example. This is an example that we have already come across in our previous video. So here we want to partition our interval into n equal parts. So if we for this we need n points, n minus 1 points in the middle of the interval and also the n points of the interval. This gives us n plus 1 points which are of this form. Now as I said, Pn divides AB into n subintervals and the length of all the subintervals are the same. And what are the length? So xi minus 1 will be equal to b minus a by n for all values of I. Now let us look at a trivial case where n is equal to 1. So we have n plus 1 points. So only the 2 endpoints of the interval, and this gives us no extra point inside the interval. So the interval after partitioning remains as it is. We will call such a partition a trivial partition. For n equal to 2, we will just have to choose the middle point. So this point is given by a plus b by 2. This point divides the whole interval into two equal parts of length b minus a by 2, b minus a by 2. Having defined the notion of partitions, we will now create our rectangles, the network of rectangles that we talked about in my previous video. So let's introduce some more definitions here. So here we are going to introduce 4 definitions: small mf, big mf, small mif and big mif. So what is small mf? So it is infimum of of all the values fx as x varies inside the interval ab. Big MF, supremum of all fx as x varies inside AB. What now you may notice that this definition, up to this definition, small mf and big mf, they are independent of any partition P. Now let us introduce a partition P x0 x1 xn of the closed interval AB, and for each of the ith subinterval I define, so this is going to be for all I equal to 1 to n, I define small m sub I of f to be the infimum of fx as x varies inside this interval xi minus 1 xi. Similarly, big MIF is defined to be the supremum of all fx as x varies inside the interval xi minus 1 xi. These are two trivial consequences of the definitions that small mf is less than or equal to small mif and big MIF is less than or equal to big MF. You may be wondering, how do we prove such kind of results? These results are very easy to derive, and I will give you a hint for the first inequality. So let me write down a far more general situation. Suppose I have two sets A, B satisfying the condition that A is a subset of B. If f is a bounded function, bounded real valued function, bounded real valued function, then if I define small mb to be infimum of fx as x belongs to B and small ma as infimum of fx as x varies inside the set A, then we will see that mb is less than or equal to ma. This result is very easy to prove. Let's see how. So mb is infimum of this set. So for by definition we see that for all x in B, mb is less than or equal to fx. Since A is a subset of B, we see that ma is we see that ma is bigger than or equal to let me write it like this: mb is less than or equal to fx for all x in A, and by taking infimum of this set we see that mb is less than or equal to ma. Now to prove this result, to prove this inequality, we just assume that A is given by the smaller interval xi minus 1 xi, which is contained inside the bigger interval AB, whose name we give it B. Now we apply the exact same result that we have proved just now, and we will easily see that this will give us mf less than or equal to small mif. You could easily derive an analogous results for supremums, and this will give us big MIF is less than or equal to big MF. I hope I am clear up to this point. So what we have proved up till now, small mf is less than or equal to small mif is less than or equal to big mif is less than or equal to big mf, and this is true for all I. Now we wanted to create two networks of rectangles, a network of bigger rectangles inside which our region would be inscribed, and another network of smaller rectangles which will be contained inside our region. So let us now formalize that notion. I define two quantities, LPF and UPF. How is LPF defined? LPF is defined by taking the sum of all the quantities small mif times xi minus 1, and UPF is defined by taking sum of all the quantities big MIF times xi minus 1. Let me try to explain what LPF and UPF are in geometric terms. So suppose this is our graph of the function y equal to f of x, and we have taken the ith subinterval. So now what we do is that we want to create a rectangle of height of height where the maximum of this function or the supremum of this function is attained. So in this interval, the supremum, in particular MIF, is being attained at this point. So the height of the rectangle is given by big MIF, and the length of the base of the rectangle is simply xi minus 1. Now what is the area of this rectangle? It is exactly the ith summand of this sum. Now what is UPF then? UPF geometrically corresponds to the area of a network of rectangles containing RF, and this network of rectangles correspond to P. Similarly, if you apply the similar kind of argument here, you will see that LPF corresponds to the area of a network of rectangles, let's say corresponding to P, contained inside RF. So here we can draw the rectangles like this by taking the smaller and smaller values in each intervals, and this will give me the total area of the network of rectangles. Now you may be correctly anticipating that the area of larger rectangles, or the area of the network of larger rectangles, will be strictly or at least bigger than the area of the network of smaller rectangles. In particular, you might be expecting that LPF should be less than or equal to UPF. This is what we are going to prove next. The proof is very easy, and you can just read from the slide. Let me not spend too much time on this, and let me go forward. So let's summarize what we have done. We have started with a bounded real valued function on a closed interval. We have introduced the notion of partitions of an interval. Given a partition, we have defined the quantities LPF, UPF. I have also told you what are the geometric intuitions for that. We have shown that LPF is less than or equal to UPF, and this inequality holds for every partition of AB. And you might be expecting from your geometric intuition that our integral, or the area of our region, should lie somewhere between LPF and UPF. Next, what we are going to do, we will refine our partitions and try to get better and better approximations for this integral which we are currently interested in. Now we will do this in our next lecture video.